By 2050, there will be a city on Mars with roughly 1 million inhabitants, a self-sustaining outpost 225 million kilometers from Earth, 8 months of travel time, one way. No supply ships, no rescue missions. This is not science fiction speculation. SpaceX has active roadmaps. The first robotic missions are targeted to launch in 2026 and could land around 2027 if Starship is ready in time. But here is the challenge that makes Mars different from every other colonization effort in human history. The colony must become completely independent before Earth stops supporting it. Water extraction, fuel production, food cultivation, habitat construction. All of it must be built from Martian resources because resupply is not an option when the nearest help is 8 months away. This is the engineering problem that will define humanity as a multi-planetary species. Let me show you how we are actually going to build it. Moon colonies could work very differently. They are 1 day of travel time from Earth, and resources are within easy reach. Colonists could return home whenever needed. Mars operates under completely different constraints. Those differences mean colonies must be self-sufficient. Current propulsion technology means about 8 months one way. Future nuclear systems might reduce that to 45 days minimum. Either way, Martian colonists cannot depend on Earth resupply. The infrastructure must harvest everything the planet offers. Water ice underground, carbon dioxide in the thin atmosphere, regolith for construction, solar energy during 12-hour days. The baseline requirement is approximately 1 million people living sustainably before Earth support ends. Whatever causes that cutoff, whether economic collapse, political decisions, or natural disasters, the Mars colony must survive independently. This drives every design decision. Surface conditions create additional constraints. Temperatures are colder than Antarctica. The atmosphere is 0.6% of Earth's pressure. Liquid water cannot exist on the surface. It would evaporate instantly. Radiation exposure is severe because there is no global magnetic field and there is minimal atmospheric shielding. The sun's radiation hits the surface directly. Outside a pressure suit, human bodies would simultaneously freeze, boil, and suffocate. Even inside pressure suits, radiation doses accumulate rapidly. This is why the first phase involves 0 humans. The first wave launches in 2026. 5 Starship landers, carrying 10 tons each. The primary objective is to land at least one successfully. SpaceX's development model accepts failure early. It relies on multiple attempts, rapid iteration, and learning through actual testing. The payload is Optimus humanoid robots. They are fully autonomous AI-powered units designed to perform tasks that humans currently do. Tesla's Robotics division, a SpaceX sister company, develops technology specifically applicable to Mars construction. Probably not coincidental. Initial robotic missions establish infrastructure, such as solar panels for power and basic landing pad preparation. But they are waiting for the second wave. 2 years later, 2028, 20 Starship landers arrive, each carrying 75 tons of cargo. This is infrastructure for human arrival. Water treatment facilities, fuel production plants, mining equipment, all installed and tested by robots before any person launches from Earth. Target location is the Arcadia region, northeast of Olympus Mons, the solar system's tallest mountain. The landing zone sits on a relatively flat equatorial plain, and large subsurface water ice deposits have been confirmed. This is the single most critical resource. Water treatment becomes the first priority. An average human requires 2 to 3 liters daily for drinking, plus additional water for hygiene, food preparation, and life support humidity. Bringing sufficient water from Earth is impractical. An 8-month journey already requires extensive recycling. Recycled water has limits because you can only process urine into drinking water so many times before molecular breakdown occurs. Water provides multiple functions beyond hydration. Electrolysis splits water into hydrogen and oxygen. Oxygen supports breathing. Hydrogen supports fuel production. This is why Arcadia's subsurface ice deposits are essential, one resource that feeds 3 critical systems. Fuel production is the second infrastructure priority. Early colonists will want return capability before permanent settlement. Starship uses methane fuel. Launch from Earth to Mars is possible with full tanks, but the return journey requires refueling on Mars because bringing enough fuel for a round trip makes the initial journey impossible. Methane is a molecule with 1 carbon atom and 4 hydrogen atoms. Hydrogen comes from water electrolysis. Carbon comes from atmospheric capture. Mars' atmosphere is 95% carbon dioxide. Carbon capture devices extract carbon for methane production and release oxygen as a byproduct, a bonus of breathable air. Mining operations support all other systems. Water ice exists underground, so subsurface extraction is required. Boring Company technology, scaled down for Mars applications, provides tunneling capability. That is an example of technology overlap between companies. Mining waste gets processed into asphalt for landing pads and roads. Nothing gets discarded. Every kilogram extracted serves multiple purposes. This is the state of Mars infrastructure, approximately 2030, 2 years after the major robotic deployment. The first crewed mission will include 100 Starship landers, each carrying 150 tons. This is when power requirements multiply dramatically. Robots will need battery recharging from solar panels, and humans will need continuous life support. Oxygen generation, water cycling, temperature control, and atmospheric pressure maintenance are all systems that must operate around the clock. A Mars day is 24 hours and 37 minutes, nearly identical to Earth. Nights lasting 12 hours require battery storage. Tesla Megapack systems, large-scale battery storage designed for terrestrial power grids, can fit inside Starship cargo bays. 1 megapack can power a small town for hours, and multiple units can keep Mars colonies alive through the long night. Habitat construction begins with Starship landers themselves. Each vehicle provides shelter, climate-controlled, radiation-shielded, life support integrated. They are not ideal long-term housing. The tall, narrow design requires elevator access and is an inefficient use of internal space, but they are functional until permanent structures are built. Permanent habitats require local materials. The glass dome concept is impractical at scale. Singapore's Airport Nature Dome covers 135,000 square meters and weighs 3,500 tons. That is 350 Starship cargo loads just for the structure, plus all assembly machinery. First-generation Mars habitats need simpler solutions. Ice dome architecture is being actively studied at NASA Langley Research Center. An inflatable donut-shaped base module forms the framework. The dome is then filled with water ice from local extraction. Ice provides radiation shielding, because water is one of the most effective barriers against solar radiation. Ice is translucent enough to allow natural light penetration, which benefits circadian rhythms and mental health. For larger structures like laboratories and factories, inflatable modules get covered with Martian concrete. Regolith mixed with urea extracted from human urine creates astrocrete, concrete stronger than Earth equivalents. The University of Manchester tested this using human blood, sweat, and urine. Medieval stonemasons mixed animal blood into mortar for the same reason. The chemistry works. Food cultivation represents the hardest challenge for self-sustainability. Bringing sufficient food from Earth is impossible at scale. A starship full of food is negligible when feeding 1 million people. Agriculture grown on Mars is mandatory. The core problem is that Martian regolith contains perchlorates, chlorine compounds that prevent bacterial and plant growth. They function like pool chlorine. Two solutions exist, and both are difficult. Either transport agricultural soil from Earth, which is insufficient in volume, or build perchlorate removal processing plants on Mars. Human waste provides fertilization. If urine can be used to create concrete binding agents, solid waste can fertilize crops. That would be complete resource utilization. Nothing is waste when everything must be manufactured locally. If these systems achieve true sustainability, power, water, oxygen, shelter, and food, all produced without Earth dependence, then Mars becomes humanity's genuine second home. Not an outpost, not a research station, a permanent, expanding civilization. Multiplanetary species status achieved. 1 million people. Complete self-sufficiency, built on Optimus robots, Starship logistics, and closed-loop resource systems. The infrastructure described is not speculative technology. It is existing hardware, scaled and adapted. Water electrolysis is established chemistry. Methane synthesis is a proven industrial process. Concrete made from biological waste has been tested in laboratories. The question is not if this is possible. The timeline is the only variable, and SpaceX is actively building toward these benchmarks. Subscribe to follow the construction of humanity's first extraterrestrial city.